Okay, let's continue and do another example. This will be a little more mathematical, but it's going to investigate something kind of interesting. What is this wave function actually telling us about, let's say, a diatomic molecule? And what is the width of the wave function, the spread of the wave function telling us? So here, we're going to switch over to the notebook and then we'll take a look. Okay, so here, let's imagine a molecule. Oh, maybe we have atom number 1 here. Maybe that's a heavy atom like chlorine, which we can assume to be like a fixed point practically. And the other is our light atom. Maybe this is hydrogen. And once we've drawn this picture, we can draw a graph of the interatomic potential. Okay, which I'm going to try and draw in here. Okay, so the interatomic potential might look like this. Most important thing is that it has a minimum. Okay, and the second important thing is that in the vicinity of the minimum, it can be approximated as a parabola. Okay, and that means that the energy states of the atom in this potential look like the energy states of a harmonic oscillator. Okay, at least at relatively low energies they do. And so finally, we can ask what the shape of the wave function is. So the shape of the lowest energy state, that wave function we know looks like that. Just going to shade it in to make it a little more visible in my drawing here. Okay. There we go. And it has a Gaussian profile. And the width of this is telling us the uncertainty in the position of the hydrogen atom in this molecule. Okay. It doesn't occupy a mathematical point in space. Instead, we can only speculate about the probability of finding the hydrogen atom at a particular location. And that probability is distributed over space as described by the probability density, which we get from the wave function. In any event, that's what it means. So let's go ahead and figure out the width of the ground state wave function for this particular case, HCl. Actually, in order to do this, it's going to be convenient to rewrite the wave function. We'll write it as C0 e to the minus x over a quantity squared. Then a becomes like an actual width with units of meters, almost like the penetration distance that we've calculated before. Okay? And so our goal will be to find out what a is. Notice that when we move away from the equilibrium position by one factor of a, the amplitude of the wave function drops by one factor of e. So that's what that's telling us. Okay, now we'll substitute this wave function into Schrodinger's equation to make it into an equation for A. So remember, Schrodinger's equation here is telling us that minus h bar squared over 2m times the second derivative of the wave function is equal to E minus potential energy times the wave function. And we know what the energy here is here. This is this is the energy of the lowest state, which is 1/2 h bar omega naught. And we also know what the potential energy is. It's 1/2 m omega naught squared times x squared. Okay? There we are. And now we have an equation for the wave function, and we just need to substitute this in order to do our problem. Okay, now the first step in this is to figure out what's the second derivative of the wave function, okay? So we can do our substitution. And I'm gonna have you show, in a reading question, what that second derivative is. Okay, so go ahead and do that question. We'll be right back. Okay, well, you should have found that the second derivative of psi here is 4x squared over a squared minus 2 over a squared times psi itself. Okay, so if we substitute this into the, oh, I'm sorry, I made a mistake. 4x squared over a to the power 4. There we are. So if we substitute this into the wave function, we have we have the following. So first, let's rewrite this as psi double prime is equal to h bar squared over 2m times, because I've canceled the minus sign, it's u minus e. Excuse me, it's 1/2 m omega naught squared x squared minus 1/2 h bar omega naught times psi. Okay. So now we're saying that 4x squared over a naught to the 4th minus 2 over a squared, that must be equal to the terms on the other side. The first term is h bar squared m omega naught squared over 4m times x squared. Oh, I noticed that the m's are going to cancel here. And the second term is minus 1 over 4 h bar cubed omega naught divided by m. Okay? Looks a little messy, but it'll clean up in just a second. So now we can do a trick. Look, we know because that the terms have to cancel in each order of x. In other words, this term must be equal to that term. And likewise, the second term must be equal to the fourth term. Because if they weren't, then if there were one value of x where they did agree, then they wouldn't agree for any other value of x. So they must agree, so they must cancel in orders of x. So because of that, we can just compare, we can just set these two terms equal and then solve for a. So doing that, we have 4 over a naught to the 4th power must equal h bar squared omega naught squared over 4. Okay, and the factors of x cancel. All right, and now we just have to simplify that to solve for a. So go ahead and do that and see what you get. And what you should find here is that a is equal to 2 h bar divided by m. Oh, excuse me 1 second. Let me stop. I apologize. I made a mistake back here. I'm surprised you didn't stop me. When multiplied both sides by 2m over h bar squared to move this term over to the other side. I didn't invert it like I was supposed to. 2m over h bar squared here. Okay? And so this was wrong also. I apologize. Let me fix that. Okay? So the second term then is m squared omega naught squared divided by h bar squared. And the last term is also wrong. Apologize. That's, oops, sorry. M h bar omega naught divided by h bar squared. Okay. Very good. And then what we find is that 4 over a to the 4th power is m squared omega naught squared over h bar squared. And then we should find that a is equal to the square root of 2 h bar over m omega naught. Ha! Apologize for the mistake, okay? But just some algebra. There we go. So what we've found here, just going to the top, is an expression for the width of this Gaussian wave function. And what it's telling us is the uncertainty, if you like, in the position of the hydrogen atom in an HCl molecule. So now we can just put in values for HCl. So then m is approximately 35 over 36 times the mass of a hydrogen atom. And then omega naught is 2 pi times 8.66 times 10 to the 13 hertz. And now we can go ahead and turn the crank and figure out the result. Okay, very good. And if you've done the calculation now, then you've found that A is approximately equal to 0.11 angstroms. So that gives you an idea. This is not the size of the molecule. What this is it's an estimate of the uncertainty in the position of the hydrogen atom in the molecule. And it's not that big, but it's also not that small. It's about 10% of the diameter of the atom. All right, well, let's stop here.